By now, you should be able to develop some reasonably complex simulation models without risk by following the steps explained in the introductory e-commerce service video. However, this is just the start. At-Risk has some amazing advanced features, and this video will explain a few of them. If you find that even these are not enough for you, you can explore the more advanced sample files that accompany At-Risk, or you can look up interesting features in the At-Risk help documents. At-Risk has many simulation settings, and although the only two you typically need to change are the number of iterations and possibly the number of simulations, you might like to learn about some of the others discussed here. By the way, don't confuse simulation settings, the current topic, with application settings. You find the application settings under the Utilities dropdown on the At-Risk ribbon. And changes you make to them apply to the current model and all future at-risk models, at least until you change them again. In contrast, simulation settings apply only to the current at-risk model. To get to the simulation settings dialog box, click this button. As you can see, the simulation settings are organized in groups, each with its own tab. In the General tab, you can change the number of iterations and the number of simulations. You can also enable multiple CPUs to speed up your simulation runs, although this is enabled by default. In the bottom section, you can change whether you want uncertain input cells to contain random values or static values, such as their means. It is actually easier to change this setting by clicking the dice button. In the View tab, the top section provides options on what you see when you run a simulation. For example, if you don't want a chart to pop up automatically, you can choose the None option. The bottom section provides other options on what you see when a simulation runs. The Sampling tab has some fairly advanced but important settings. I will discuss only the top section. Also, the settings you see here are good ones, and I recommend using them. There are two sampling types, Monte Carlo and Latin hypercube. The difference between them is subtle and difficult to explain. A couple of the example files in the At-Risk Features group shed some light on the difference. However, the bottom line is that Latin hypercube sampling yields much more accurate results, and you should definitely use it. Mathematicians and computer scientists have devised many ways of generating random numbers on a computer, and At-Risk implements several of them, as you see here. They differ only slightly in their statistical properties, and any of them should work about equally well for your simulation. The Mersenne twister is a favorite of many simulators. The initial seed governs the stream of random numbers generated in a given simulation. If you select the Choose Randomly group, you will get slightly different results each time you run a simulation. If you choose a fixed seed, you can choose a positive number as the seed that starts the stream of random numbers. Any positive integer would work. By using this same seed, you guarantee the same stream of random numbers, and hence the same result on different simulation runs. This might be useful if you want to replicate your results at a later time. Finally, if you run multiple simulations with the risk SimTable function, you should make them all use the same seed. Then each simulation will see the same random numbers, which typically leads to a fairer comparison among them. The Macros tab is for advanced users. It is possible, and sometimes very useful, to write macros that perform various tasks before, during, or after a simulation is run. This tab lets you implement this. Of course, you have to write the macros in Excel's VBA macro language. The Convergence tab is also for advanced users. The chances are that you will never need to change any of its settings. Some of these simulation settings can be changed with the buttons in the simulation group. See the At-Risk tutorial Word file for explanations of these buttons. If a model has several uncertain inputs and you enter an at-risk function such as risk normal in each of their cells, the inputs are treated as if they are independent. However, quantities in the real world are often correlated to some extent, either positively or negatively. If you know that inputs are correlated and you can measure the extent of their correlation, you should account for this correlation in your model by using at-risk's risk-cormat function, where cormat is short for correlation matrix. It is usually difficult to gauge how much this actually matters. This depends entirely on the specific model, but there is no excuse for assuming independence when you know that it isn't realistic. In the model shown here, I will illustrate how to do it. This model assumes you are going to invest certain percentages of your wealth for some period of time, such as a year, in two stocks and a commodity, such as gold. You get to choose these percentages. For now, they are assumed to be 30%, 20%, and 50%. The returns are assumed to be normally distributed with the means and standard deviations given. For example, 5.5% and 8.5%. For now, each group of green cells is identical. Each has the same normal distributions. It makes sense that the asset returns might be correlated. For example, the two stock returns might be highly positively correlated, and they might each be negatively correlated with the commodity return. Starting with the normal distributions in row 14, I will now build in correlations in the middle group. The easiest way to do this is with at-risk's Define Correlations button. Select the cells you want to be correlated, in this case the returns, and click the button. In the resulting dialog box, you provide a name for the correlation matrix, such as Core Matrix 1, and a location for it to be placed. Then you enter the correlations you want to use. Actually, it suffices to enter only the correlations below the diagonal. Here I will use 0.8 for the correlation between the two stocks, and minus 0.6 and minus 0.7 for the correlations between the stocks and the commodity. These would typically be estimated from historical returns on these assets. When you click OK, the correlation matrix appears, and the formulas in row 14 change automatically. They now have a third argument, the risk-cormat function. Its first argument is the name of the correlation matrix, and its second argument is the index of the return. The first stock has index 1. The second stock has index 2. And the commodity has index 3. The green cells in the left group do not have this risk-cormat function, so they are generated independently of one another. For the sake of comparison, I will now build in all positive correlations to the group on the right. One of the most important tasks in developing an at-risk model is finding appropriate probability distributions for uncertain inputs. You can sometimes narrow the choice by assessments such as the quantity must be between 0 and 100, or the quantity can have only a few discrete values, or the distribution of the quantity is skewed to the right. Any such assessment narrows the choice of appropriate input distributions. For example, if you believe that it makes sense to use an input distribution that is heavily skewed to the right, this rules out symmetric distributions, such as the normal distribution. Another approach is to fit possible distributions to historical data on the quantity. Of course, historical data are not always available, but when they are, at-risk has a very powerful distribution fitting tool that can be used. This tool fits various candidate distributions to the data and ranks them on their goodness of fit to the data. From there, you can make the ultimate choice of the distribution you want to use. As an example, the data shown here contains 3 years of weekly demands, 156 observations, for a company's product. If a simulation model requires demands in one or more future weeks, it is natural to use a probability distribution that fits the historical data well. To find good fits, click the Distribution Fitting dropdown on the At-Risk ribbon and select Fit. In the resulting dialog box, you first define the dataset, including its type, in the Data tab. Note that the label at the top of the data should not be part of the data range. Next, you need to select candidate distributions you want to try in the Distributions to Fit tab. Specifically, once you make some choices about the data in the left side of the dialog box, for example, you know the quantity has a lower bound of 0, but you are unsure of the upper bound, At-Risk automatically checks all the continuous distributions that satisfy these conditions. If you have never heard of some of these distributions, feel free to uncheck them, as I will do here. When you click the Fit button, At-Risk fits each of the checked distributions to the data. Note that each checked item is really a family of distributions. For example, the log normal family has 2 parameters that specify any particular log normal distribution. Because log normal is checked, At-Risk finds the 2 parameters of the log normal family that best fit the data, and it does this similarly for the other checked items. Then it ranks the best fitting member of each family on their goodness of fit to the data, and it shows you the results graphically and numerically. As you can see, the fitting is very fast. At-Risk actually has 5 criteria. There were only 3 criteria prior to version 6.0 for ranking the distributions. These 5 criteria usually give very similar rankings, but they aren't necessarily identical. For comparisons of fits, the 2 new criteria, AIC and BIC, are preferred. Using either AIC or BIC, gamma is ranked first, slightly ahead of Weibull, log normal, and triangular. The exponential and uniform fits are not nearly as good. You can see the fits in the graph, where each curve is a theoretical distribution, and the blue bars represent the histogram of the data. Note that the best gamma fit has parameters 2.5657 and 41.566. At this point, you could enter the risk gamma function with these parameters into a simulation model as the demand for some future week and feel comfortable that you have chosen a reasonably good probability distribution for demand. At-Risk makes this very easy with its Right to Sell button. By the way, At-Risk remembers any datasets that have been defined for fitting. To see them, click the Distribution Fitting dropdown. Any defined fits are listed at the bottom, and you can open any of them and modify them if you like. Starting in At-Risk 6.0, there is also a batch fit tool in the distribution fitting group. This tool allows you to fit several distributions all at once. This not only saves time, but it allows you to estimate correlations between the variables. Then these fits, along with their correlations, can be used in a simulation model. Here is an example with 4 columns of historical data on 4 related variables. Each column has 150 observations. To batch fit these data, you select Batch Fit from the Distribution Fitting dropdown and fill in the dialog similarly to the case for a single fit. Now there is also a Report tab. If you select the Live Report option, the estimated fits will change automatically if any of the data change. I will illustrate this shortly. Also, you can accept the checked Include Correlations option to estimate correlations between the variables. After clicking Fit, in the resulting fit summary sheet, you see the best fits along with the correlations. In fact, most of your choices in the dialog are encoded in the formulas in row 9. To enter these in a simulation model, just copy and paste. Then, to see that these are really live, change one of the data values. You see that the formulas update automatically. The introductory e-commerce service video illustrated the powerful risk SimTable function. This function allows you to run a separate simulation for a list of values in some cell, often corresponding to a decision variable. But what happens if you have 2 or more such cells, each with its own list of possible values? Can you enter a risk SimTable formula in each of them? You might expect this to run a separate simulation for each combination of values. For example, if there are 4 possible values for the first cell and 3 for the second, you might expect this to run 4 times 3 or 12 simulations. It turns out that this is not quite the behavior you get. Fortunately, there is a method for getting at risk to run 12 simulations, 1 for each combination of values. This worksheet shows how to do it with 2 variables being varied. The same idea carries over to any number of variables you would like to vary. You should first list the combinations of values you want to test, as in rows 4 and 5. In this case, each of 4 mean values will be paired with each of 3 standard deviation values, so you should set the number of simulations to 12. In general, this table of combinations can have any number of rows, 1 per variable, and any number of columns, 1 per combination of values. Then you use a separate risk SimTable function for each variable with argument equal to the entire corresponding row of the table. Now when the 12 simulations are run, the summary statistics at the bottom indicate that the risk SimTable functions are working as expected. It would be tempting to list each possible mean only once and each possible standard deviation only once, as indicated in the red cells. However, this would not get you the results you'd expect. In general, if you set the number of simulations to a number n greater than 1, then when at-risk runs simulation k, it uses the kth value in each risk SimTable function it finds. For example, on simulation number 3, it uses the 3rd value of each risk SimTable function. If a risk SimTable function has fewer than n values, the corresponding simulations have errors. For example, if you have a risk SimTable function with 2 values and you set the number of simulations to 4, the 3rd and 4th simulations will have errors. If you have a risk SimTable function with 4 values and you set the number of simulations to 2, the 3rd and 4th values will never be used. Again, the risk SimTable function is very powerful, but it's easy to misuse it when you want to vary multiple variables. Therefore, make sure you use the method shown here. You might be familiar with Excel's GoalSeek tool. It is used for solving one equation in one unknown. Specifically, it allows you to force a formula cell to a desired value by varying a selected changing cell. For example, in a break-even model, you might want to find the sales volume required to break even, that is, to force profit to 0. This is a perfect use of Excel's GoalSeek tool. At-Risk has its own very similar GoalSeek tool, found under Advanced Analyses dropdown. The difference is that it uses a changing cell, called an adjustable cell, to force a summary measure of an output cell to a desired value. This summary measure could be the mean, the standard deviation, a percentile, or others. As an example, suppose you want to find the capacity in the early e-commerce model, shown here, that forces the mean profit to $230,000. You might remember that this mean is about $200,000 if the capacity is set to 2 million. I will show this by running the simulation again. To force the mean profit to $230,000, select Goal Seek from the Advanced Analyses dropdown and fill in the resulting dialog box, as is done here. The goal is to force the mean of cell C15 to 230,000 by changing cell C10. You can speed up the search slightly by adding lower and upper bounds on the capacities to search in the options dialog box, as I will do here. The bounds have been set at 1 million and 2 million. The tighter the bounds are, the quicker the search will be because at-risk will have less area to search. Also, note in this dialog box that only an approximate answer is guaranteed. The mean profit will be within 1% of the value desired. The reason is that it might take too long to find a more exact value. Now back out of Options and click Analyze. You see the result of Goal Seek for this example fairly quickly. The Goal Seek solution is a capacity of slightly more than 1.2 million. Of course, this doesn't mean that a capacity of slightly more than 1.2 million will always lead to a profit of $230,000. It only implies that this capacity will lead to a mean profit of approximately $230,000. As you see, with this capacity from Goal Seek, the mean profit, found with the risk mean function, is very close to $230,000. The risk sim table function is often used to test several values of a decision variable so that a best value can be found. At-risk's Risk Optimizer tool can be used to take this a step further. It allows you to maximize or minimize a selected summary measure of any at-risk output cell by varying selected adjustable cells, where adjustable cells refer to values you are allowed to vary to optimize the summary measure. For example, you could maximize mean profit, minimize the standard deviation of profit, or maximize the probability of making profit greater than $220,000. This video provides only a quick glimpse of Risk Optimizer. It is a very powerful tool, and an entire chapter of a book, or even an entire book, could be devoted to it. To see more, you can examine the many Risk Optimizer examples that accompany at-risk. First, if you are used to earlier versions of at-risk, you should realize that Risk Optimizer is now totally incorporated into at-risk 6.0. You don't need to load it separately into memory. It is in the Tools group of the at-risk ribbon. To use Risk Optimizer, you must first set up an optimization model. This will be done for the same e-commerce model you have seen before. To proceed, click the Risk Optimizer dropdown on the at-risk ribbon and select Model Definition. You then fill out the dialog box as will be done here. You must specify whether to maximize or minimize, an output cell, a summary measure of that output to optimize, and there are a lot of choices, any adjustable cells and bounds on them, and any other constraints. In this model, I will maximize the 10th percentile of profit by letting the capacity vary from 1 million to 2 million, and there are no other constraints. When you click OK, nothing happens, at least not yet. This model definition dialog just stores the settings. To actually perform the optimization, select Start from the Risk Optimizer dropdown. Risk Optimizer can take some time to converge to an optimal solution. This is because it systematically checks many values of the adjustable cell or cells, and for each it runs a simulation, so be patient. However, it shows you the progress in various ways, including the progress indicators shown here. Specifically, the last two boxes show the starting and current values of the objective, in this case the 10th percentile of profit. Often fairly quick improvements are made at first, but then they level off and it seems that the optimizer is spinning its wheels. Once you sense that no significant improvements are being made, you can click the Stop button on the bottom right and accept the best solution so far. Normally I would let this run a bit longer, but to save time I will stop it now. If you like, you can ask for a summary of the final solution, although I won't do it here. I will just ask for the best solution so far, which is the default. Here you see the best 10th percentile of profit so far in a blue box and the corresponding capacity that achieved it. Again, Risk Optimizer is a tremendous complement to At-Risk. At-Risk performs simulations, and then Risk Optimizer uses the results of these to optimize some function. Just be aware that it takes some time. A lot is going on behind the scenes.